Here's an example of how to calculate the rate constant K, M, and N. That's the reaction orders with respect to each of the reactants. So we're dealing with the same reactions we were in the first mini lecture. In the first mini lecture I actually gave you what the values of M and N were. Now we're actually going to go ahead and find them. And the way we find them is by doing a bunch of experiments, and these experiments will vary the concentrations and see what kind of initial rates we get for these reactions. Well, let me give you some sort of context for what initial rate means. So here's an example of a reaction, and we're looking at the concentration of the reaction over time. And as we expect, what happens if we start out with a 0.1 molar concentration of a reactant, the concentration will decrease as the time increases, and that's what we would expect to have happen. Now, the other thing we expect to see is that we can figure out what the rate is based on the change in concentration over the change in time. So that's a situation where we're looking for the slope or the gradient, which is the change in y over the change in x. So what we're looking at here is the initial rate. This is at the very beginning of the reaction, and of course what's going to happen is that the rate will be faster at the beginning, that is, the slope will be greater at the beginning than it will be towards the end of the reaction. Now the reason for that is that as the reaction goes on, the amount of reactants in the reaction will decrease, and therefore the rate of any reaction will also decrease. That's why the line is not straight, it's a curve. And we can see the changes in the slope that occur as the reaction continues on. But all we're interested in here is just an approximation, and the approximation will be gained by looking at the initial rate, or the rate at the very beginning of the reaction, which will be gained by taking the concentration over the change in time, or change in concentration over change in time. Alright, so we can see that that's what our experiments will be measuring. Alright, so there's our experiments. We're varying the concentrations, and what we're finding is these initial rates after we've started with these initial concentrations. Now what we've purposefully done here is made some of the concentrations the same and then made some of the concentrations different. This allows us to see what effect changing the concentration of one will have on the initial rate while keeping the other one constant. So what we're looking at here is a situation where we're going to compare experiments, that is, put one divided by the other and see what we can come up with as far as M and N go. So the smart move here, if I was interested in finding the value of N, would be to choose values of these two, of the HgCl2 here, that will allow us to cancel those out. So we're looking for concentrations that are the same. So I can use rate 1 and rate 2, or I could use rate 3 and rate 4. It really wouldn't matter. I could use either set of those. I'm going to choose rate 1 and rate 2. The other thing I want to look at here is to look at the initial rates and figure out what I'm going to put over the other. The smart move here would be to put the bigger one over the smaller one, because I'm going to end up with whole numbers rather than fractions. That'll just be a little bit easier for me to work with. Now, it's not impossible to do it the other way, but why make life for yourself more difficult? So what I'm going to do is I'm going to put rate 2 over rate 1, and here's how it's going to look when I put in the initial calculations. So I'll have rate 2 equals K, and it'll be HgCl2 to the power of M, and I'll put a 1 subscript there because we're dealing, whoops, 2 subscript here because we're dealing with the second experiment. This is the one we're looking at first. And then it'll be C2O4, whoops, C2O4 to minus to the power of N, and again another subscript of 2 down there. And I'll put that over rate 1. See, we're comparing now rate 1 and rate 2. And you can see we're doing the same thing again. I'll use a subscript of 1. And then it's just a matter of plugging in our values. Rate 2, 7.20 times 10 to the negative 5. molar per minute. I'm just getting that reaction. I'm just getting that unit from up here in the table. And 1.80 times 10 to the negative 5 molar per minute down here equals K. Okay, and the HgCl2 here is going to be 0.105. I will put that in there like that, 105, and that's the M, and 0.105 again. So those are going to be the same, and we'll have the 0.300 up the top here to the N, and 0.150 to the N down here. So what you can see here is that the K's will cancel, these units here will cancel, and this will cancel as well, the 0.105 to the M and the 0.105 to the N. So what we'll be left with down here is, if we do the math here, well, that comes out to 4, and we've got 4 equals 2 to the power of N. That's 0.300 divided by 0.150. So you can see here that what's going to happen is we need a value of N that will allow us 2 to the power of what gives 4, and that value would be 2. So our value for N is going to be 2 in this instance. Alright, so we've got N under control. Let's see how we might figure out what M is. And now we've got to choose a different set of experiments because we want to find the value of M. And M will be found by choosing 2 values or 2 experiments that will allow us to cancel the C2042 minuses. Now I can choose rate 1 and rate 4, that would work, or I could choose rate 2 and rate 3. I think I'll choose rate 2 and rate 3 this time. So rate 2 equals K, HgCl2 to the M. I'll put a 2 down there because that's the second experiment. C2042 minus the value of N. And remember here, the reason I've chosen rate 2 over rate 3 is because that's going to allow these two to come out to a whole number as well. Alright, same deal. And I'll put a 3 down here, C2042 minus. So that's 2. It comes with 2. Whoops. And we've got the M down here. So now we can go ahead and plug in our values again. So we'll have 7.20 times 10 to the negative 5 molar per minute over 3.60 times 10 to the negative 5. And we're going to go ahead and sub in our values again. And we'll have 0.0520 down here in this instance. And you can see that what's going to happen is that these two values are going to end up cancelling. K's will end up cancelling. These will end up cancelling. And what we'll end up with is 2 equals, well, it's not going to be exactly 2, but it'll be approximately 2 to the power of m. And this will give me a value of m equals 1. And it's worth saying that m and n are generally going to be whole numbers, so we don't have to work with exact numbers here. As long as we can get a whole number for m and n, we're good. Alright, so now we've got values for m and n. We can now go ahead and calculate out a value for k.